Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all to lecture number 30 on the subject of computer organization and assembly language programming. The title of today's session is Structure of x86 64 Assembly Program. Well, in the last session we discussed the tool chain and programming environment and also wrote, assembled, linked and executed our first Hello World assembly program, first.nesm. And today we are going to do a scuba diving in the first.nesm source file. We will discuss the assembly language instruction format and the overall structure of assembly program, including the contents of section.data, section.bss and section.text. We will also understand how the move and the syscall instruction of x86 64 work. So let's start playing. First of all, let us have a quick recap of the toolchain and the programming environment. Remember, first of all, we need to write the x86 64 assembly code using our text editor like gedit, notepad or vim. We can use code editor like atom or sublime, and we can also use some IDE like sesum, eclipse, xcode or visual studio. Well, I have not gone into the details of what all these assembly instruction means, and that we will do today in a little while. Anyway, after we are done writing this code in a text file, we need to assemble it. And the assembler we are using in this part of the course is the net wide assembler nesm. Once we give this command, we get the first.o file in 64-bit executable and linkable format. Then we use the GNU linker LD to link this first.o file with the standard C library and generate the final executable named myexe. And finally, on the Debian based operating system Kali Linux, we loaded and executed this program. Well, dear students, as far as debugging and reverse engineering is concerned, we will do that using GDB with PIDA plugin, strace, objdump and read ELF commands in some future session, inshallah. Now let us do a scuba dive in the source code of first.nesm file. Well, dear students, there are three types of statements in assembly language programming, and typically each statement should appear on a separate line. The first type is the x86 64 assembly instructions. These instructions are actually converted into machine code and when executed instruct the processor what to do. Some x86 specific assembly instructions are move, syscall and maybe add, sub, mul and div. The second type of instruction are the pseudo instructions. These are not real x86 machine instructions but are normally used in the real instruction field. Some nesm specific pseudo instructions are db, dw, resb, resw, equ. We have used this db and equ over here. The third type are the assembler directives. Assembly directives are the statements that direct the assembler to do something. The speciality of these statements is that they are effective only during the assembly of a program and they do not generate any machine executable code. And some NASM specific directives are section, extern, global, bits, and so on. You can see the section directive over here and the global as well. Well, dear students, the general format of an assembly instruction consists of 4 fields: the label or a variable, mnemonic, operand, and comment. Well, a label or a variable name which marks the address of a memory location are shown over here. Message is the variable name. Xstat is a variable memory constant, not a variable, rather memory constant. And this underscore start followed by a colon is a label. Then we have the mnemonics, which can be an assembly instruction like the move and the syscall over here. It can be a pseudo instruction like this db or equ, and it can be an assembler directive like this section and this global over here. Then we have operand, which specify the data required by the operation. Well, operands for assembly instructions can be a register as shown over here, RAX, RDI, RSI. It can be a memory variable like this MSG. It can be a memory constant like this exit status or xstat. And it can be a numeric constant like this one over here. The number of operands entirely depend on the instruction. For example, this move instruction has 2 operands, while this syscall instruction is a 0 operand instruction. And finally, we have comments. A comment begin with a semicolon and end with a new line character. They can be placed anywhere, including after an instruction or maybe in the beginning of the program. Well, these comments are ignored by the assembler. Well, dear students, a properly formatted x86 64 assembly source file normally has 3 sections. And the first is the section dot data. All initialized data like memory variables and constants are placed over here. The next section is section.bss. All uninitialized data is declared in this section, and this in our file first.nasm there is nothing in the BSS section, so this can be ignored. The third is the section.text, and the entire code of your assembly program is placed in this section. So these are the 3 sections of an assembly program: section.data, section.bss, and section.text. And now let us discuss the contents of these sections one by one, and let us start with the section.data. Well, dear students, whenever you want to define a constant, you use this EQU directive, followed by the value, which can be a numeric or maybe a string constant. Over here you can see the EQU is followed by a numeric constant, that is 54. Well, dear students, numeric constants may be specified in decimal as over here 54, maybe in hex or octal, and the default is decimal. If you want to specify in hex, you precede this number with 0x. For example, 127 in decimal can be represented in hex as 0x7f. And similarly, 511 in decimal can be written as 777Q in octal over here. Last but not the least, before this EQU directive, you mention the name of the constant. And over here, the name of the constant is exit underscore status. Well, remember the value of a constant cannot change during the program execution. The name of the constant is substituted for the defined values during the assembly process. That means once we assemble this file, wherever in the code section you have this exit status constant, in our case over here, it will be replaced with the value of this constant, that is 54. Okay, then comes the variables. Well, the define directive sets aside storage in memory for variable. The general format for the variable declaration is variable name, defined directive, and then its initialized initial value. And in case of arrays, it may be comma separated multiple values. For example, the MSG over here is the name of the variable. This db is the NASM directive defined byte, and this string learning is fun with Arif are the bytes of data that we are defining. Remember, each character in this string is a single byte. So L is a byte, E is a byte, A is a byte, and so on. And at the end over here, this hex A or decimal 10 is the ASCII of new line character. And also note that the length of this string LEARNING space and so on is 26 bytes, including this new line character. Well, dear students, NASM provides various directives for reserving storage space for variables, and that is given in this table. DB define byte, DW define word, DD define double word, DQ define quad word, DT define 10 bytes, and DO is for IEEE 754 128-bit storage space. Please do note that each byte of character is stored as its ASCII value in binary, and each decimal value is stored as 16-bit binary equivalent. In this architecture, negative numbers are stored as a 2's complement representation, and real numbers are stored in IEEE format. Well, this slide shows you some example variable declarations with different defined directives. You can define a byte, a string, a 16-bit, 32-bit, or 64-bit integer variable, an array of bytes, and floating point values as well. Okay, let's move on to the next section, that is the .bss section. Well, all the uninitialized data is declared in this .bss section, block storage start, and we use the res directive, reserve directive, to reserve the uninitialized space in memory for our variables. And the format is variable name, the reserve directive, and then the count of the values we want to put in inside this variable. NASM presents various reserve directives like RESP is for reserve byte, RESW is for reserve word, and so on. And these are some examples. For example, BARR is the name, RESB is the directive reserve byte, and this 10 means we want an array of 10 elements, each of size byte. And similarly, this WARR is the name of the variable, RESW is the directive reserve word, and this 50 means we want to create an array of 50 elements, each of 16 bits or a word size. And remember, these variables will be placed in this part of your process address space, the uninitialized data section. And in this code, since there are no variables declared with the reserved directive, so there is nothing over here. In our future sessions, we will use this part of the assembly code as well. Okay, we move on to the section dot text now. Well, dear students, first of all, let me talk about this label underscore start colon, which is the entry point of every assembly program. The way a variable is the named memory location containing data. This message is a named memory location containing this data. This label is again a named memory location containing the address of an instruction. Upon assembling, the assembler will replace all the occurrences of the label with the corresponding memory address. The text section or the code section will always include at least one label named underscore start or maybe main. The Linux linker LD expect the program entry point label with the name of underscore start, as I have used over here. And if you are using GCC instead of LD to link your program, GCC expect the program entry point label with the name of main. This global is again a directive that is used to define a symbol. So this global underscore start basically defines a symbol named underscore start. And we have used global over here because we may want that this underscore start is expected to be used by some other module using the extern directive. And the extern directive is used to declare a symbol which is not defined anywhere in the module being assembled, but is assumed to be defined in some other module. We will come on to this extern directive when we will move on to assembly programs that will be composed of multiple .o files. Okay, now let's talk about the move instruction. These are the move instructions which we have used in our assembly program, and these move instructions are used for moving data from one storage space to another. And the general format of a move instruction is shown over here. It takes two operands, move destination comma source. And remember, both the operands of move instruction should be of the same size. And after this move instruction, the value of the source operand remains unchanged. And of course, the destination is replaced with the value inside the source operand. And the move instruction in x86 64 may have one of the following 5 forms. Move register comma immediate, that means this instruction, this is the register operand, and this is the immediate value that will be placed inside this RAX after this instruction executes successfully. Move register comma register, there is no example of register comma register in this program, so we can move the contents of RBX to RAX. For example, move RAX RBX, so RBX contents will be moved to RAX. Move register comma memory, if you want to move the memory contents to a register, you use this format of the move instruction. Message is a memory location, so the address of that memory location will be moved to RSI. So this move register memory is related to this part of the instruction. Move memory register, if you want to move the contents of a register to a memory location. And move memory immediate, if you want to move some immediate value to some memory location, you use this form of the move instruction. And remember, using move, you cannot move one memory location to another memory location. That is not allowed in x86-64. Okay, so after the move instruction, we have the syscall instruction in our code. Well, dear students, there are two methods using which your programs can request the operating system to perform a privileged operation or a service like printing a message on screen, as done over here, and maybe reading from the keyboard. This can be done using a system call or maybe a library call. And over here in this program, we are using the system call. And remember, a system call is a controlled entry point into the operating system code, allowing a process to request the OS to perform a privileged operation. In simple words, remember, system call is just like a function call. The only difference is that the code of the system call is not inside the user space, rather that is inside the operating system kernel space. Okay, so let's go into the details of how a system call is made. First of all, what are the available system calls for an operating system? Remember, dear students, every operating system has its own set of system calls, and every system call has its own associated ID. On my Intel Core i7 CPU running Kali Linux 5.3, there are total of 433 system calls, and you can see the list of these system calls as well as their associated IDs by viewing this file. Inside USR include x86-64 Linux GNU, ASM, and the name of the file is unistd_64.h. I strongly recommend that you should view the contents of this file on your Debian based OS and see how many system calls you have. I have mentioned few calls over here. For example, the read call has an ID of 0, the write call has an ID of 1, and so on to the exit call has an ID of 60. Remember, this read call is used to read the keyboard, this write call is used to write on maybe the std out, and this exit call is used to exit the program gracefully. Okay, so now the question is how to make a system call. While the first step is depending on your hardware architecture, you need to place the system call ID in an appropriate register. And if you are using x86-64 architecture, the system call ID needs to be placed inside RAX register. And if you are using the 32-bit x386, the system call ID needs to be placed in the EAX register. And if you are using the ARM CPU, the system call ID needs to be placed in R7. And if you are using this ARM 64, the system call ID needs to be placed in X8. Okay, so the next step is to place the system call arguments in appropriate registers. So if you have x86-64 CPU, which we are having right now, and you want to pass arguments to the system call, so you can pass 6 arguments to the system call via registers. So the first argument need to be passed in the RDI register, second RSI, third RDX, fourth R10, fifth R8, and sixth R9. So these are the 6 registers in sequence in which you need to place the arguments that you want to pass to your system call in case of x86-64 architecture. And I have also mentioned the registers in case of other architectures as well, but we are just interested in this. Okay, so after the system call is done, the return value of the system call can be found in this register RAX. In case of x86-64 architecture, once the system call has been made, the return value will be placed by the operating system inside the RAX register. So you can check out the contents of the RAX register if you are interested in the return value of the system call. Okay, so before I go into the details of this code, let me summarize again what I have said is, in case of x86 64 architecture, we need to place the system call ID in the RAX register, and if you want to pass arguments to that system call, we need to place the arguments inside RDI, RSI, RDX, R10, R8 and R9 registers. Okay, so let's talk about these 5 instructions now. And these 5 instructions actually display a message on screen. And the message is learning is fun with Arif. And this message is placed inside the memory, and the address of the memory where this data resides is MSG. Okay. So this is actually the system call that I have written in the C syntax that we want to call. And this write system call is passed 3 arguments. The first is the file descriptor. The second is the buffer in which the data is there. And the third is the count, that is the length of this string. Okay, remember dear students, this file descriptor is actually an integer value that is pointing to the particular file where we want to write. And remember, there are 3 file descriptors that are always available to every program, and they are 0, 1 and 2. The 0 file descriptor points to the keyboard. The 1 file descriptor points to the standard output or screen, and the 2 file descriptor points to the standard error, that is again the screen. So since we want to write a message on standard output, so over here we need to place a 1, and this is the string where we want which we want to print on the screen, and the address of this string is MSG. And then here we have to mention the count of the characters inside that string, and the count of the characters LEARNING and so on to this new line character is 26. Okay, so as we have seen on the previous slide, the ID of the write system call is 1, so we need to place 1 in the RAX register, and this is what we have done over here. Move RAX, 1, that is place 1 inside the RAX register, and remember this 1 is the system call ID of write. As far as the first argument is concerned, we need to place the first argument in the RDI register, and this argument is the file descriptor. And since we want to write on the screen or standard output, and the file descriptor of the standard output is again 1, so we have moved or placed 1 inside the RDI register. The second argument is this buffer. We need to place the address of the string inside RSI register, and the address of the string is MSG, so we need to place MSG in RSI. So this is the instruction which do this task. Move RSI, message. The address of the string which we want to display on screen will be moved to RSI. And the third argument to the write system call is the length of the string, which we have counted from here is 26. So we need to move 26 inside the RDX register, which is the register containing the third argument to a system call. So this is the instruction move RDX26, which will place the length of the string inside the RDX register. So the stage is set. We have moved the ID of the system call in the appropriate register, and we have moved the arguments to appropriate register. And now we want to make the system call. So this sys call is the instruction actually which is going to make the system call. And the same procedure will be followed in case of if we want to exit the program gracefully. Remember, in C, if you want to exit the program, the system call you want to make is the exit system call with one integer value, that is the exit status. From the file I have mentioned on the previous slide, you can check out the ID of the exit system call is 60. So we need to place the ID of the system call inside RAX register. So this is the move instruction which places the ID of the exit system call inside the RAX register. Then we have placed the status, that is the only argument to the exit system call, which is this 54, inside the RDI register. So once again, these two move instruction will set the stage right for the exit system call, moving the system call ID inside the RAX register and the only argument inside the RDI register. And after this, we just need to make this instruction, that is syscall instruction, and this syscall instruction will of course execute the exit system call. Okay, so I think I have made to my maximum the concept clear, and if I have missed anything, please let me know in the Dropbox. If you still have any confusion, let me know in the Dropbox of the YouTube channel of this video, and I will respond to your question. And I tried my best to make you understand every bit of the first.nesum program. And I hope this session was informative for you all. If you all have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.